test. It really doesn't matter the exam inside.
You ever had an oral test before?
A world test?
Oral.
Oral test?
Yeah, it's much harder.
Very hard. Can you have an oral chemistry test?
Oh yeah.
Oral anything test.
My qualifying exam for PhD was oral.
Ooh. What did you do? How'd you do it? What's an oral?
I passed.
You passed?
I'm guessing you passed.
Yeah,
He's
on
here.
the first time.
What is it like? Are you just like speaking?
It's next door. PD's
Okay.
next door.
Hey.
Are you just speaking like dimensional analysis, like verbally? Is like that what it is, or?
I had so there's two parts to it, and the test takes anywhere from an hour to 3 hours, and it was me, then 3 professors, not my advisor. The first part was on my research, and I gave a brief presentation. Then they could ask any question they wanted, and then I had to come up with I had to do take an article, like a recent article, and then talk about it, and they could ask any questions about that. And the idea is like if I'm really focused on my research, on my stuff, and then the article will say, okay, do you have breadth in chemistry? And it was pretty gruesome. I had nightmares about it a month after I passed.
Did you
Got
pass with
PTSD.
a passing grade, or did you pass with like an above average grade?
You pass or you don't.
Oh, okay. It's like senior project.
Yeah, it's your you go from a graduate student to a PhD candidate. At least that's what they do at Berkeley. Berkeley is weird. It's very traditional. You call everyone professor too. You don't use doctor or anything. It's almost like Hogwarts. And they treat you like crap. Not that I'm bitter or anything. Okay, 3 o'clock, time to start. You might see me limping around today. I rolled my ankle on my jog this morning. I hope I didn't break it, but we'll find out. But I'm fine. I'm going to survive.
You could have canceled class.
And they wouldn't have paid me. They dock my pay if I cancel class.
They paid you to be here?
What's that?
They paid to be here?
Yeah, I know. It's funny how it works that way. Come on, though. I mean, what would I do if I didn't see your guys' beautiful faces? You know?
You'd cry.
I
That's
would.
okay.
I'd cry. I'd be on
I
the
would
couch with my foster kitten, watching Netflix and crying.
Foster kitten. No.
I actually have a foster kitten right now.
So you're fostering it to adopt it, or you're fostering it for somebody else?
It's something that we do to volunteer.
What's his name?
Aw, I want to do it with dogs.
Can you name it?
It came with a name. This one's name was Julius, but we've been calling it Pikachu. I'll show you pictures.
My cat
Is
is
this
awesome.
why you
Are
always
you gonna
send
do
us
this?
cat
I have a
pictures?
video.
I've been trying to I've been trying to take a month off of cats because my teaching evaluation said I'm tired of seeing cat pictures. So
Oh my god, what an asshole.
That's so rude, yeah.
That's so rude.
hey, you know,
That was something constructive.
I
Start
close the
taking pictures of
loop.
the dogs.
You know, it's closing the loop. I'm doing my part. You know, taking the teacher evaluations and giving the students what they want. So, all right, but we start today with a problem.
I thought you
So,
were showing us cat pictures.
I'll show you my
I thought
phone.
we were throwing out all of classwork today.
Oh, we are. Well, if it's fun, it's not really work, right? And isn't this fun? Isn't this fun?
No!
Are you having the best time ever?
More fun if we look at cat pictures.
I'll show you some cat pictures. Okay. Methane plus water makes carbon monoxide and 3 hydrogens. We have methane at 25.5 liters, 732 torr, 25 degrees Celsius. Water at 22.8 liters, 702 torr, 125 degrees Celsius. It makes hydrogen at this 26.2 liters, 764 0 degrees Celsius. And here's R, here's the P equals RT, and that should be Kelvin. Otherwise, it's a straight line. Kelvin is degrees Celsius plus 273. So what is the percent yield of this? This is a limiting reagent theoretical yield percent yield problem, except using gases. So have to take all the stuff you learned from the first test, and apply it to this stuff. So it never goes away. And what do? You have to figure out what the theoretical yield is. You have to figure out the limiting reagent, the theoretical yield, and then the percent yield. So tell me, can you just look at this and tell which one's the limiting reagent? I can. Do you know why I can tell? Compare methane. Methane has got more volume, it has higher pressure, and it has lower temperature. So for the number of moles, so more pressure means more moles, more volume means more moles, and it's inversely proportional here, and in T, R is a constant, right? If T is up, N is down, that's inversely proportional. So all these indicate that water has got fewer moles than methane. But I'll start you off.
It's so
So now you have to do it for water. So, your turn. Can you read it? Is it two?
zoom in a little bit.
Well, if I zoom in, then you lose the. You can do this. Got a lot of pictures of this puzzle. Alright, here's my foster cat.
Aww. He's so cute. Do you have any animals of your own?
No.
Do you want any?
Maybe.
You want my dog?
For real? I'm looking for a dog. Is it a
Yeah.
No, if anything, I keep this fuzzball. I'm more of a cat person.
Really?
You never, yeah, I never had guessed that.
My chest.
Hey, look at that. That's what you
I
mean.
heard that word a long time.
She's not Jessica's.
Chest.
She's super cool. She's like a full-on cat.
Okay, so after you do that, so N is moles, N H2O times 3 moles hydrogen to every mole water. This equals your theoretical yield. And then your percent yield is going to be your actual of your theoretical times 100% equals the number of moles of hydrogen over the number of moles of water times 3. You get the number of moles of hydrogen from here. So your NH2 is pressure of volume, so 760 times atmosphere, 760 volume, 26.2, 08206, 273. Are you doing any
What happened to the screen?
You want me to zoom back?
That was so What happened to the screen?
What zoom do you want on it?
No, that's fine now. We're golden.
Okay. No, here, you follow what's going on?
I'm trying to pull a collection.
You doing okay? You have any questions? Yeah. Did you actually buy that? No. No, because NASA is very strict. You're not allowed to buy. You're not allowed to. Well, you can't put your emblem on anything without permission.
They sell all that kind of stuff at Paxson.
They do.
It's just like a thing.
They must. I think they must have a deal with NASA then.
Yeah.
I mean, seriously, because they'll come after. It's like Disney.
He'll be after you, girl. You better watch out.
Well, no, they won't be after her. We have to attack her.
I'm pretty sure that.
What?
Six
Yeah,
minutes.
it's.
Oh,
Yeah.
that
I don't know.
No, because I was on a grant and someone made NASA shirts and NASA threw a hit because he did.
Well, there's just no word going on these
NASA and Disney scare me.
Oh, you've worked with NASA before?
No,
Okay.
this is just in general.
They're scary.
Yeah, well, it's like Disney. Disney is like in control of everything and anything. They have Star Wars and Marvel. Like, what would they need with that? Like, what do they want with
I
that?
thought NASA wasn't a
They
thing.
came out with this thing called Disney Plus, and it's like
Yeah.
Netflix. Do you know how much it is a year?
It's like, isn't it like
Yeah, they
$10 a
took all
month or
the
something?
Disney
Huh?
movies off
It's
of
like-
Netflix.
It's like $7 a month, and it's like $70 a year. So.
Oh, really?
Yeah, but like you're able to see like everything.
Yeah, they're
that
trying to
they
put
own.
Netflix out of business.
I think they are because they own National Geographic too.
Oh, they do?
Yeah, they do.
Holy crap.
Yeah,
They're gonna buy the BBC next?
Disney's a monopoly. They truly
Well, it's
are.
not yet.
Well,
They
it's
have
good.
Touchstone Pictures, they have Pixar. That was, Lucas did all that stuff. He made Pixar.
Really?
Yeah, well, originally.
Oh.
His special effects company that he used to make Star Wars became Pixar.
Mhm.
Or at least part of it, the computer animation part, because there's still Lucasfilms Studios.
Yeah.
And Disney bought that for like, was it 1 or 2 million? I forget. Chump change. Well, my point of this, I know it's sorry if I'm being cruel to start a class this way. Can't forget anything.
How'd you get 0.645?
Being loud. How did I get 0.645?
Is-
That's weird.
Here's my paper.
760. You have one over 760.
Oh, okay. So,
Clearly it was my thing.
okay, so I calculated the number of, what'd you call that? CH4.
Moles.
No, what is the CH1?
CH4 limiting reagent. Then CH4, that's just an example. I was going to show you how to do it for the nitrogen or hydrogen.
Moles of that, we find the moles of the water, and moles of the hydrogen.
Yeah, the limiting reagent is water.
Hydrogen.
Limiting reagent is water. And then, so from that, the theoretical yield is 3 times that. So it's 1.93. It's because there's 3 moles hydrogen every mole of water,
Okay.
right? And then you got to figure out the actual yield, and so the number of moles of hydrogen is 1.17 moles. So you get 1.17 moles, and you should get 1.93. That's 60%. Wow, you're amazed.
No, I'm just
What's in that Red Bull?
Red Bull. Tomorrow's 7 days for me.
Okay. So, are you guys following? I wanted you to work on this a little bit. So for this one, it's a limiting reagent problem. And although you could tell by inspection that the limiting reagent is water, but if you didn't know, you could calculate it out. There's 1 mole methane, 0.645 moles hydrogen. So that means hydrogen is the limiting reagent because it's 1-to-1 ratio for both. And theoretical yield is 3 because there's 1 to 3 for both. So the theoretical yield is 3 times 0.645, which is 1.93. And then you got to figure out the actual yield. So the number of moles of hydrogen at that pressure, temperature, and volume is 1.17. So 1.17 over 1.93. So the actual over the theoretical, that times 100% is 60%. Well, it's 60.5, but 60%. Questions with this? So remember, can't forget anything. Does anybody, let's change topics. Anybody have any favorite guilty fast food? What's your guilty fast food that you like?
McDonald's.
Okay, what's your favorite thing?
Double cheeseburger.
Double cheeseburger. How many calories in a McDonald's double
Oh
cheeseburger?
my god, please don't tell me.
Oh, it's healthy.
Yes. That's why I'm still so thin.
It is merely 437 calories.
That's not bad. I got like 4 or 5.
Does that mean that every single double cheeseburger is 437 calories?
Yes.
No.
No. There's a distribution. They haven't drew a distribution, right? So there'll be a number in the calories and the peak is at 437, right? So why am I doing this? Because similar to that, we have temperature. So for temperature, I have to bend over this desk so far. Temperature is average kinetic energy. And at a high temperature, I'll show you better pictures later, at a lower temperature, you have distributions. You don't just have a single item. Just like with the number of calories in a fast food item, there's a range and there's a distribution. Same thing is true with velocity, and so let's just say, so number and then speed. Speed is just the absolute value of the velocity. So depending on the temperature, and higher temperature means faster moving, in generally speaking.
Yeah.
Okay, and we're going to talk about next is kinetic molecular theory, and this is what the basis is for the ideal gas law. So tell me, what do you think the perfect man or the perfect woman is like? What is the perfect man like? What's the perfect woman like? I mean, we have that in art and beauty, right? And actually, it changes. If you notice, I used to work at Victoria's Secret in the corporate offices, and contemporary sense of beauty is very different than older sense of beauty. So if you study art and you know about the Renaissance, the most beautiful form was an 18-year-old ripped man. So if you've ever seen any of Michelangelo's paintings and sculptures, like they all look like David. So David was like a sculpture of David. That was the most beautiful human form. It was a skinny, muscular 18-year-old man. And if you go to the Sistine Chapel, The women were basically ripped 18-year-old men with breasts. And Moses, he has a sculpture of Moses. Moses was a ripped 18-year-old man with a beard and horns in his head. Because they thought, yeah, it was a mistranslation in the Bible. They thought that Moses had horns in his head. So men were considered beautiful, and women were considered dirty and disgusting. And then you have contemporary sense of beauty, and there's been like a cultural shift, right? Now it's the younger pubescent female is the most beautiful form, and men are disgusting. So it's kind of been like we've changed. So, but that's like we say, what's the perfect beauty kind of thing, and that's one of the things that Victoria's Secret tried to do. Like they played on that, and like if you look at the pictures, I watched them doctor it. I was an intern there, and like they would take the photographs of the women, and they would, the Victoria's Secret models, they're people. They have wrinkles, they have pimples, they've got blemishes, all sorts of things, and they put a ton of makeup on them, and then they airbrush all the photographs, so they're not real. It's interesting though, right now, with our generation, Victoria's Secret is becoming less mainstream, and they're I don't want to say they're losing money, but they're losing shares of the market. They're still a very profitable business, but there's not as much as a powerhouse as they used to be back in the 90s and the early 2000s. So, but that's how things change. So, but that's the idea. They tried to pick the most beautiful thing, the perfect thing of beauty. So, and now instead of people, let's talk about gases. What is the ideal gas? So, and these are postulates. A postulate is something that you take. It's a mathematical expression. A postulate is a mathematical expression that you accept without proof. So these are the postulates for the ideal gas law. We'll connect back to their theory, which is where we derive the ideal gas law. The size of a particle is negatively small. So this is the first postulate. The idea is that the gas particles themselves have no size. So, that's something that doesn't exist. Also, well, the kinetic energy of the particle is proportional to the temperature. That's the definition of temperature, so that's true. 3, collision of one particle to another or at the walls is completely elastic, meaning there's absolutely no attraction. So like if you have two particles, they're flying around like this, and if they attract each other, they'll hold hands and they'll kind of fly around like this. So instead of having 2 moles of particles, now you have 1 mole of particles. So they have to completely have no attraction for each other whatsoever. That's the ideal gas right there. So that's our made-up thing. Oh, and then later on, in a few minutes, I'll talk about root mean squared velocity. So has anyone here taken physics yet?
Mm-hmm.
Yeah, so 2 people. Velocity, I don't know why chemistry uses U. We should use V like the rest of the frickin' world. But chemistry uses U for velocity. Can velocity be negative? Yes, it can. Velocity has magnitude and direction. Direction can be negative. So how do you get rid of a negative velocity? You square it. So any negative number squared is a positive number. So you square it, and then you take the average of that, and then you take the square root of that. And that's the root mean squared. And there's a derivation there. It's a 3RT. The root mean squared velocity is 3RT over the molecular weight. Okay, so as promised, here are the prettier pictures. So looking at this, we have the relative number right here on the y-axis, and then velocity. In this case, it's all positive, so I guess it would be absolute value of velocity on the x-axis. And notice a few things. And so this is all the same temperature. And notice, so oxygen is 32 grams per mole, nitrogen is 28, water is 18, helium is 4, hydrogen is 2. The heavier gas particles, they have a narrow distribution and relatively lower speed. And then the lighter ones have a much broader distribution and they have higher speed. So that's what it means when you have gases in the same temperature. The lighter ones are moving faster, and the heavier ones are moving more slowly, on average. But the other thing to note, there's a little bit of the gas either way that are moving very, very slowly. So I'll talk about more of that later. But there's a whole distribution, and some of them are actually not moving at all. And within the same temperature, so we talked about different gases. How about the same gas at different temperatures? So y-axis is number. Oh, this is nitrogen as well. Okay, so this is nitrogen. This is the number of nitrogen molecules, and here's the velocity right here. And notice that the cooler temperature is a very narrow distribution, and the higher temperature means a more broad distribution. Has anyone ever gotten to Calc 2 yet? No, you haven't. The area underneath the curves for these three, it doesn't look like it's drawn to scale, but it should be the area in each of these curves. It looks like that's true for this one. I don't know about the red one. I guess it could be. But the idea is the area underneath the curve is the same for each of these. So if you do integration on this. Okay, but so what? Why do we care? One of the things I mentioned that with vapor pressure last class, that there's, depending on where you're at the temperature, that you're going to have a certain fraction of particles that can leave the vapor phase from energy. The other one that we're not going to talk about till next semester is energy, activation energy for chemical reactions. There has to be enough energy for a chemical reaction to happen. And if you take something like this book right here, this book right now is burning. It is actually it is oxidizing. Like, have you ever seen really, really old books? They burn. They're getting burnt. So if you look at this at 273 Kelvin, so that's what 0 degrees Celsius. So if it takes this here blue line to actually have a chemical reaction, there's a really, really tiny fraction of gas here that has enough energy to react. So I know this is nitrogen, but if this is oxygen, this book is burning. It is burning. If you see old paper, it is being burnt. But then again, if you look at 2000 Kelvin, that's around 4,000 to 5,000 Fahrenheit. So that's like a welding torch. How long would this book survive if I stuck it with a welding torch? Right, you know, a minute if we were lucky. Right, this thing with that much energy, that would react very quickly. Why? Why does it take 1,000 years for this thing to burn at this temperature, and it takes a minute for it to burn under a welding torch? Well, it's because look at this. Look at the fraction here in this yellow line of gas particles that can burn. So because there's enough energy here, there's a lot more collisions, a lot more effective collisions that are undergoing chemical reaction. And whereas at this temperature, it's really, really slow because there's not a whole lot. So that's some of the so whats, and those are some other future items we'll talk about. Then I mentioned that there's also a small amount that are not moving at all. And gas particles are flying around. They're flying around, and what do? Some are moving fast, some are moving slow as a distribution, and sometimes they collide. They collide, and this one's colliding, and that one, it moves away. Now this one's not moving. So this one's at 0 velocity, but it gets collided. So it's not like it's always at 0. It just is at 0 until it gets collided by another one. But there's always a small percentage of something that's not moving in that. So I wish I had a good demonstration for that other than just my hands flying around. Okay. So I mentioned this, the root mean squared velocity. And here's the derivation for it. I don't want to go over it too much. Sorry, my ankle hurts, so I'm sitting down. And the equation comes out to be the root mean squared velocity is the square root of 3RT over the molecular weight. And the most common mistake students make in this one, they use the wrong value of R. It has to do with the units. I'll show you what I mean by the units here. Oh, and I guess I should have mentioned the root mean squared velocity. These are the points I noted with the blue. So this area right here, that's what the root mean squared velocity is. That that max peak for each. Okay, so let's do this. What's the root mean squared velocity of oxygen at 25 degrees Celsius? So root mean squared velocity, the equation is 3RT over molecular weight. And what's weird about this, we have to use molecular weight in kilograms per mole. I'll show you the units. So this is equal to 3 times R, 8.314 units joules per mole Kelvin. Temperature is 298 Kelvin. All of molecular weight, 0.032 kilograms per mole. And you know that raised to the 1/2 power, same thing as square root, right? At least I hope you know that. All right, let's look at units. So equal D, this means dimensionality. So kelvins cancel, 1/moles cancel, and we're left with joules per kilogram. So the unit on a joule is a kilogram meter squared per second squared. So the way I remember, you'll be given this, so you don't have to memorize that. But the way I remember it, a Newton is a force. Have you guys taken physics yet? Some have, some haven't. But you don't have to have physics as a prerequisite for this class. So of course there's physics in it, but it's very small amounts. But a Newton is a force, and a Newton is, so force is equal to mass times acceleration. So like a kilogram, this is about a liter of water, although the aluminum is heavier, but this is about a kilogram of water. And then with a acceleration of 1, so that would be acceleration is the second derivative of displacement, so it's with respect to time. So it would be mass kilogram times the acceleration would be a meter divided by second squared, because that's the second derivative. And then you have, so that's a Newton, and a joule is energy. Energy is force over the path length. So a joule is a Newton times a meter. So a Newton is a kilogram meter per second squared. So a Newton meter is a kilogram meter squared per second squared, which is what a joule is. So, and you don't have to know that for this class. That explanation, that's just to show you where I'm getting these. So this is a kilogram meter squared per second squared all over kilogram, square root. And the kilograms cancel. So kilograms cancel. And we're left with the square root of meter squared per second squared, which is meters per second. And then we plug this into our calculator. All right. Calculator. 3 times 8.314. Actually, you know what I should do? I should just put the whole thing in square root. And this is equal to 482 meters per second. Oh crap, I should have used it. It's a fuzzy picture. Fuzzy kittens are okay. Fuzzy pictures, not so much. At least that's my mantra. Alright, last class I was having a hard time wondering how I calculated that, so that's why I take a picture. So I guess in a way you guys are lucky you get the, I've already rehearsed this lesson to the morning class.
You
Okay.
get the improved lectures.
Yes. All right, and there's also more students in the morning section. At least more students. I guess there's more students enrolled in that one too. But so you get more individual time as well. Anyways, 482. That's half a kilometer a second. That means a mile every 3 seconds, right? So that's pretty darn fast, right? And
You can run that fast.
you can run that
I
fast.
can.
Oh, you can. It's okay.
I can.
I'd be impressed. If you did, you would create a sonic boom. This is faster than the speed of sound. And this is also the average. That means there's molecules that are moving faster than this. So that, so an oxygen particle, one that's hitting you right now is going, it can go, a mile in 3 seconds. That's pretty fast. Why isn't there a sonic boom? Why aren't we constantly hearing all these little tiny sonic booms? Because the sound wave, the air itself is the carrier of the sound wave, so it's the medium. And also the oxygen's not massive enough. So have you ever heard a sonic boom before? You haven't. They're loud. The fighter jets, it's kind of cool. And it cracks like kind of going through. But, oh well. Where did you hear a sonic boom?
Oh, I did.
Oh, you did?
Like I know of one.
Oh, okay.
Videos.
Does it have to be a big object?
Yeah.
Not like
Oh, not necessarily. Bullets create sonic booms, so do whips. That's a sonic boom. And same thing with bullets. Well, I've never heard a bullet whiz by my head, though. So I've fired a gun before, but I haven't been shot at.
Me too.
But apparently you can hear it whipping by.
That's also how you go deaf.
With fire.
You could probably go deaf if someone's shooting a bullet next to your ear.
Oh yeah, absolutely. Yeah, I know it's loud. You definitely, if you ever go to a shooting range, you definitely need earplugs. But okay. So that's root mean squared velocity. Next idea is talk about gas's path. So the mean free path, that's how far a gas particle can go without going into a collision. And something to note about gases, though, they're flying around. And if you do this, one of the things you have to do is you have to make sounds while you do it, because the gas particles are going to go. Makes more sense if you make the pew sound. Right? So, but the idea, though, is the gas is moving around. If it's in a container, it's striking the walls, it's making all sorts of, well, not really sounds, but it's striking other things. And and they're moving fast, right? So a mile every 3 seconds. So they're moving fast. And also, this is where the pressure comes from. Pressure comes from these collisions with the wall. And a single oxygen atom or molecule is not very massive, but it is going fast, but the momentum's not that great. But then again, if you have a large number, and if you sum up all those collisions, then yeah, you get a pretty strong pressure from that. And with this mean free path, next thing we're talking about is known as Graham's law of fusion. So the idea with this, what is a fusion? If you have a container and you poke a hole in the container, the lighter gases, because they move faster, so lighter gases are, so here's a heavy gas. Brr, 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 brr. Lighter gases, right? So it's going really fast. And the lighter gases, because of that, they can travel through a hole in the container much more quickly. And Graham's law of diffusion said that the rate of this diffusion is 1 over the square root of the molecular weight. And if you remember that the speed, the velocity is the square root of 3RT over the molecular weight. And also, Graham's law of fusion further said that the difference, if you have one rate versus the other rate, is the square root of the second over the first. So if you have the rate of the first over the second, the square root is the inverse of that, the second over the first. And so why do we care? So do you ever have to put air into your tires? There should be no reason why you would ever have to put air in your tires here in Hawaii. If you ever live somewhere on the mainland where it snows, in the wintertime you have to put air in your tires because it loses pressure from the temperature. In the springtime you have to take air out of your tires, otherwise they'll blow up. So, but here in Hawaii, you should never have to put air in your tires. But the air does seep out though, over time, right? The air does sometimes seep out. And it's because it diffuses through tiny little cracks in your tire. So it's not a perfect seal. Also, those birthday balloons, the ones you can get like with the helium, do they even sell those here? I don't think I've seen them. They do, okay.
Yeah.
I guess I don't hang out with many kids. I guess that's a good thing. But they, nowadays they use those metallic ones. They used to use just plain old balloons, and those things would get droopy after a day or two. At least the balloon, like the metallic ones, they last for like a week or two, kind of thing. But eventually they start getting droopy and they don't work anymore, right? So why do they get droopy? Well, because it's not a perfect seal, and the helium is seeping out through like usually the bottom, tiny cracks, and even so, it can go through the plastic. Can we get perfect seals for things? Yes, we can. They're pretty expensive. When do we do something like that? Like International Space Station, something like that it's worthwhile doing really, really tight seals on things. Although the International Space Station is not a perfect one either. They have metal seals. Although in a vacuum, metal can fuse. Certain metals will fuse in a vacuum. But okay, so then that's a fusion. And then the other what with this, this is how we enrich uranium to make fuel for nuclear power plants and for nuclear weapons. And I'll talk about that a little bit later. Okay, so unknown gas fuses at a rate that is 0.462 times that of nitrogen gas. So calculate the molar mass of the unknown gas. So rate A over rate B is the square root of molecular weight of B over molecular weight of A. So we know this is 0.462, and this equals the rate of your unknown. I'll just use the X. The rate of X over rate of nitrogen, and equals the square root of nitrogen. So the molecular weight of nitrogen is 28 grams per mole, and this is our unknown there. So we have 0.462 is equal to square root of 28 over x. So we square both sides. 0.462 squared equals 28 over x, and then x equals 28 over 0.462 squared, and this is 131. And this is likely xenon. Xenon is 131 grams per mole. So that's how you solve a problem using Graham's law of fusion. So questions with this one? I guess I didn't do a recap of the last one. So shoot. All right, I normally would have to do this problem, but I realized this is. The answer is A for this one. This is how we enrich uranium. Well, there's a couple ways you can enrich uranium. Well, there's only two ways. You can do it this way. Well, I guess there are a couple. You can vaporize the uranium. That takes a lot of energy. This is how we do it. In Brazil and also in Israel, they use lasers. So you can use lasers to vaporize uranium and then have them fuse. But if you follow your politics, right now there's some strife going on with Iran and also with the nuclear treaty. And before that, Iran was saying like, oh, we're not making nuclear weapons. And so here in the United States, we typically enrich our uranium. So if you dig uranium out of the ground, it is 0.7% uranium-235. In our nuclear power plants, we enrich it to somewhere between 3 and 9%. So we have 106 functional nuclear power plants in the United States, and we have 106 different designs for nuclear power plants. We are actually really stupid the way we do our nuclear power. We don't have a set design at all. And it depends on which one they have. They have different designs. They use different enrichments as well. But one thing about that, when in Iran, they found uranium in excess of 20% enriched. You need, what's that?
Big difference.
Yeah, but then to make a nuclear weapon, you need like 99%. So you need it really enriched. So, but yeah, but Iran is saying like, oh, we're not making nuclear weapons. The truth of the matter is, either they are galactically stupid and they hate money and they hate safety, or they're making nuclear weapons. So like a nuclear power plant core, like if like a half a gigabyte would probably be about 4 times the size of this table, like 4 times the volume of this table would be about the size of a nuclear reactor core. They're not that big. Well, I mean, depends on your definition of size. In a nuclear submarine uses weapons-grade plutonium. The core is about this big. It's about 1 liter or 2. It's not very big at all. So why do you need to have a really small core in a nuclear submarine? Because of space. What's that?
Nothing.
Space. Space is an issue. But having a really enriched fuel core is a problem because it can melt down really easily. So you have to make sure the heat leaves a reactor very efficiently. Whereas if you have a big reactor, if you have a nice big reactor, you can put a lot of space in it and it's easier to keep it cooler. So it's much easier to run a big reactor than a small reactor for nuclear power. And they actually don't run them that hot. They run them about 500 degrees Celsius, which in a candle flame is hotter. So they don't run nuclear power plants very hot because you don't want them to melt down. Because if they melt down, it can get really gnarly. So in a civilian power plant, and you're not on a nuclear sub, space is not an issue. So having a bigger core that's less enriched, that has a lower energy density is better. It's safer, it's cheaper, and it's easier to work with. So yeah, Iran's either stupid or they're making nuclear bombs. Yeah, of course they're making nuclear bombs. Duh. So at least Iran is, they're trying to be sneaky about it. North Korea just out says, yeah, we're making nuclear weapons. The uranium bombs are easier. Are you guys interested in nuclear weapons at all, or is it? I don't know. I started out grad school as a nuclear physicist, so I know a bit about nuclear weapons. And nothing I know is classified. I'm not a classified person at all.
Have you ever seen a nuclear weapon?
I never have, no.
Me either.
Me either.
Has anyone ever seen? Well, I guess you can't really say if you've seen them.
Really?
Some of the replicas of the little boy and the Batman.
We're in Hiroshima or
Los Angeles.
Los Alamos? Oh, really? Okay, I've never been to Los Alamos.
So why are other countries not allowed to make nuclear bombs, but we are?
We're not okay. So
America.
right now, the nuclear countries. So part of it has to do with politics. The UN has 5 countries that are considered the member states that have absolute veto power. It's United States, Russia, Great Britain, France, and China. So, and they're all nuclear powers. Also, Pakistan and India have nuclear weapons. They have about 150 each. Israel is a nuclear power. We gave them their nukes. They have about 150. South Africa used to have nuclear weapons. They denuclearized.
Everybody's
Smart.
demon.
Smart. I know. I don't even know why we have.
The idea is a deterrent. China's making more nukes. We have a series of treaties with Russia.
Pulling out of
Yeah, there's a lot of treaties with that. We used to have around 30,000 nuclear devices. Right now we have 6,000.
Compared to other countries with only 100.
Yeah, United States and Russia has the most. And and we had stupid nuclear weapons too. I mean, they didn't make any sense. So uranium bombs, they're the easiest to make, at least as far as like constructing them. Like the one, Little Boy was a uranium bomb, and the way that worked, you had a cylinder with a hole in it and a plug, and the gunpowder shot the plug into the cylinder to create a critical mass. Critical mass for uranium is about 50 kilograms, so about 110 pounds, and it's about this big. So plutonium, on the other hand, critical mass for plutonium is 5 kilograms, which is about 11 pounds. It's about the size of a softball. Problem with plutonium, though, it's the rate of spontaneous fission, so it's really high. So if you try to do the plug into the uranium bomb, it doesn't work. You have to have explosives that compress it down. And the explosives, the amount of material is not classified, but the manner in which to compress it down is classified. North Korea is trying to do that. They haven't done it very effectively yet. All their bombs have really fizzled.
What is tritium injection?
So that's I think we talk about when North Korea said they have a hydrogen bomb. I don't think they have a hydrogen bomb. I think they have what's called a fission boosted device, where you have tritium, and that increases the yield of the nuclear weapon. It can increase the yield up to 100 kilotons of TNT.
How does that increase the yield?
It has more neutrons. Yeah.
Explosive.
More neutrons. More neutrons because the neutrons, the way that the nuclear works is it'll absorb, so you have a nucleus absorbs a neutron, and then it releases something called the pairing energy, because you have an odd number of neutrons, so it pairs the other neutron and it releases the pairing energy. So imagine like a droplet. It excites a droplet, then it gets excited and it splits and fizzes, it splits in half, and that releases energy. It releases neutrons, which then are absorbed by other ones, and they split. So
it's like the chain reaction.
Chain reaction, yeah. There's more neutrons for the chain reaction. It makes the bomb more powerful. It also makes it more green and clean. Has less radioactive fallout. So, but the North Korea's weapons are not that effective. Like if one blew up, they blew up one at Costco, it might take out Krispy Kreme, but we'd probably be okay here.
Isn't one of the limiting factors like the precision of the machines that you have to use to make the bombs? You have to have super precise machinery.
For the explosions, yes, because you have to have the explosions they have to compress. You have to compress the plutonium down. So if it's misaligned,
Yeah.
then it'll fizz.
Like the fire.
It won't misfire. It'll they call fizzle. So
That happened in a Tom Clancy movie.
it's the rate of spontaneous fission of plutonium is really high, and which means it generates more neutrons by itself, and in doing so, that will make the chain reaction too fast, and it'll burn out too quickly before it's like if you had a pile of gunpowder and you're trying to make it fuse, it'll like spark up around the gunpowder, but then it won't light the main charge. So then it'll fizzle real fast, explode, and it won't reach the proper critical mass. That's the danger of it. But it makes the plutonium bombs are better than uranium bombs, they have. We had nuclear grenades. I mean, you can get one that's only slightly heavier than 11 pounds. I mean, can you imagine throwing something? You could maybe shot put something like, if you're really good, 50 feet, right? But I mean, what hole are you gonna duck under if you have a nuclear grenade that has a massive yield, then that's your nuclear grenade. Part of it was a strategy. If USSR was going to invade Western Europe, they're gonna wait till like their tanks and army went over, and then they'd blow up a bunch of small yield nukes. But I know that West Germany probably wouldn't have liked that, or East Germany probably wouldn't have liked that. But hey, yeah. So yeah, that's what's going on with the world today, I guess. Believe it or not, we're actually better. I mean, we've done some really stupid things.
Well, like looking at Syria.
Well, that's a different. No, I mean like as far as nuclear weapons.
Well, I read that there's an air base in Turkey that has like 50 nukes.
Yeah.
Yeah.
Yeah, we have nukes deployed all over the world.
Yeah.
Yeah.
So, but now
They're holding it hostage. From what I understand, they're saying if you remove those nukes, then we're gonna make our own.
yeah, or do they like consider the alliance broken up that pull out?
Yeah.
America's so good at keeping treaties.
Well, it used to be.
Never. Never,
Yeah.
actually.
Well, kind of the law goes Constitution, then the laws, then the treaties. So I guess treaties are kind of considered to be lower in our own recognition of the law. Treaties are like the lowest form of law, whereas the Constitution's the highest form of law. But I don't know. But yeah, America.
Cool.
But okay, so that's
Pressing.
nuclear. Sorry if I'm. Did anybody have any questions about nuclear weapons or anything like that? The sort. I can keep on talking about nuclear weapons, but I think they're kind of cool. Well, they're fascinating, I should say. I've never seen one go off. Well, we haven't blown.
Well, okay, can you explain thorium reactors? Why is that? How's that
A
different?
breeder reactor?
Like, yeah.
So
Thorium reactor, it's a different. They use thorium instead of uranium, right?
yeah,
And how does that work?
that transmutates. So it'll. Thorium is right here, and if it absorbs a neutron, absorbs a neutron, it can beta decay to, I don't know what PA is. Then it can turn into uranium, and uranium is an element that can undergo. If it's an odd number, it can neutrons. It's a nuclear fuel. So the idea of the thorium is going to absorb energy, or absorb the neutrons, and then become uranium, and then that it's a breeder reactor. It's a reactor that generates its own fuel. So that way, and there's a lot more thorium around than uranium.
Where do you get thorium? Do we use it for anything now?
We used to use it for lantern mantles. You ever seen the gas lanterns, a little white mesh? That used to be thorium. Now we use cerium for that. Let's see here. What do we use thorium for? This guy tell us. There's more thorium than there is tin. Okay, we had thoriated toothpaste. Oh yeah, welding electrodes. Oh yeah. Has anyone ever done TIG welding before? So TIG, tungsten inert gases. I've used thoriated welding tips before. Thorium has a really high melting point, named after Thor, the thunder god. So TIG, so tungsten inert gas. If you have a really high with a high temperature, you can get you can have tips that are thoriated, and they're really good. They're thin, and they're pretty easy to work with. They're easier to work with than the tungsten ones. Problem is they're radioactive. And the way TIG welding works is you have a current that runs through something, and then you spray inert gas like argon, and then if you're welding something, you take the tip and bring it close, and then you can see like the electricity go through, and it'll melt everything around it. So I've done that before for sculpture. And I remember when I was taking the class, the teacher took the thorium tip, like, oh, this is Dole, and she went and started like grinding it down on a spin wheel, and I remember I took a jump back because thorium is not a big deal if it's outside of your body, but if you breathe it in, it's bad news bears. That's lung cancer got written all over it. So I actually went and took a Geiger counter and swept around to see if I could find anything. Actually, I couldn't find anything. So, but it's what's that?
Someone read it in there.
Yep, that's why I took a jump back. Because it's also with exposure, it's distance squared. So if your distance squared, so if you double your distance, you decrease your exposure by a factor of 4. So anyways,
Did you tell her after?
I decided to sweep it first. It was kind of hard to talk to them about chemicals because they had no idea what was dangerous and what was not. I don't know if they thought it was weird in that class because I always wore a respirator, like the ones that you get for silicosis. So when they used what's it called, garnet sprayer. It sprayed garnet sand at particles. I forget what it's called. It's a way of cleaning something. But they're like, okay, well, put on your mask. Like this teacher said, just don't bring the stuff in. And then she put a scarf over her mouth. I'm like that doesn't stop anything, right? So I didn't, and so I just went in. I'm like, this is stupid. I just went and bought one of the 3M whatever respirators that block everything. I just use that. No, because people, if they work around the dust like that, the metal dusts, I mean, you can get like a cough and stuff from that. People don't like that. And then I was just like, all right, well, I've got a PhD, I should use my brain.
Yeah.
But then again, they had like pump sprayers, and they're saying, oh, be careful, these are chemicals. And the pump sprayers, though, the particle size of the pumps when you spray it in the air, the particle size is not enough that it won't get past your sinuses. Besides the fact the stuff they were using wasn't that dangerous anyways, but they were always so afraid of the pump sprayers. And I didn't even put on my gas mask when I used that stuff. But I don't know. I mean, I tried talking about that, like, guys, this is actually okay. Like, oh, it's chemicals. But then again, they're welding with radioactive stuff and grinding metal that's radioactive. I'm like, I don't know. Then again, not like I didn't think stupid. I've already injured myself once today. All right. The stuff about nuclear weapons is not on the test. Or about Iran. Nor this stuff. Or does anybody have any questions about things? I'm just going to cover this really briefly.
No, go.
So this is not on the test, but let me talk about real gases. So ideal gases, they are just like the Michelangelo sculptures. People don't really look like that, or the Victoria's Secret posters. Those are all, those are basically imaginary. So is an ideal gas. There is no such thing as an ideal gas. About as ideal as you can get, though, is helium. So if you see here the ideal gas, and this is at 1 atmosphere, 273 Kelvin. Ideal gas has 22.41 liters, and everything is about that. Helium is spot on. Hydrogen's a little bit more, but they're really close. And I told you before that gas at this temperature and pressure acts fairly ideally. When do gases not act ideally? Well, high pressure. If it's under high pressure, you have gas under high pressure, there's a lot of gas particles bumping around. And gases themselves, the atoms, have a little bit of volume. And that little bit of volume is an issue. So at higher pressure, the volume is higher. So the ideal gas under high pressure, a real gas is going to have a higher volume because of the fact that the gas particles themselves have volume. And the other thing is that at low temperature, so at the idea that everything is no attraction is a completely static collision. So think high temperature, all they're just bouncing off. There's not enough time for things to hold hands. They're moving too fast. If you're sprinting, it's really hard to hold hands with your partner. But if you're moving really slowly, it's really easy to hold hands with someone. So that's how the same thing works with atoms and molecules. When they're moving really slowly, then they can kind of get close to each other, then feel the attraction, and then they can hang out together. And when they do that, it's seen, instead of having 2 gas particles, it's like 1. So because of that, the pressure is lower than predicted because it's like there's less particles. And then there's the van der Waals equation. And this is what the textbook says is the best way to deal with real gases. And I bring it up because it illustrates what an ideal gas is and what it isn't. This is also a really terrible way to do real gases. So here's the van der Waals equation, here's the tabulated data on that. The better way to do it, there's 2 ways. Probably the best way is to look up things that are referred to as the COX or Cox charts. And this is just a bunch of data. So you can just look up the real data, and there's books and books of data. And the other thing you can do, there's a PV equals Z nRT. And you introduce a new variable here. This is called a lumped sum approximation. So it means we know it's not perfect, so we take all the variables and we throw it into one variable and we just make it work. And then you create what's called a semi-empirical, semi-empirical, sort of experimental model, semi-empirical model. Ideal gas law, it's a mathematically derived model. It's like string theory. String theory is mathematically derived. It has no sense in reality whatsoever. Same thing with ideal gas law, completely made up. But a lot of other things we have, we take everything into a lump sum approximation. An example of that is friction. Have you studied friction before? So friction, like I'm running it together in my hands. Friction is supposed to be, the friction is a coefficient of friction times the normal force, is what they say the friction is. And is that what the friction is? No, it's not, actually. If you want to calculate the friction, you have to take my hands and you have to look at the position of each of the electrons and all the atoms, and then you have to look at the attraction repulsion of this, and then you got to move it, and you got to do it again, and again, you have to do it for each position as it's running. And the surface of my hand is not smooth either, so it's going to change each and every time. That would be the friction. That's way too hard. The amount of computer power to do that is immense, and you'd have to use a computer. You couldn't do that by hand. Well, I guess you could, but you'd need an army of people to do one calculation. So what do? Well, you take a bunch of data, and you do it over and over again, and you find a trend, like, oh, if we take all those variables and we just put it all into one thing, and then we figure out that it works for a certain range over a certain material, and then, hey, it works, we're just going to go with it. And we do this over and over again. And if you ever, does anyone here want to be an engineer? I think there's a few engineers here. Yeah, just one, huh? If you'll see this all over engineering. So like heat transfer coefficients, that's a lump sum approximation. Many things. They just take equations, like, hey, we found this equation works for this range, and here's this value, and here's the value, works for this range, and you don't use it. And you do that a lot for engineering. And then you just have to manage the error with that. So those are better ways to do it. And this is using the lump sum approximation is better to do for real gases. It works better than the van der Waals equation, to be honest with you. But the textbook is not very practical. It's not more of a showman kind of chemist than a practical chemist. That's okay. I've never met Tro, though. I wouldn't mind meeting him, but it's one thing about living in Hawaii. Anyways, anybody have any questions? Real gas is not on test. Nuclear weapons not on test. If anybody has any questions about nuke stuff, feel free to ask. I actually do know quite a bit about it. Oh, and if there ever is a nuclear blast, if you're wondering, stay inside for 2 days and you're probably fine. So believe it or not.
If your
Oh
house
yeah,
is
I
on
forgot
level.
about that. I forgot the fallout.
Yeah.
Yeah. Radiation.
Yeah, there's something called the law of 7/10s. So after 7 hours, the radiation goes to 110. So then 7 squared, so it's 49 2 days. It goes to 1/100. And 7 cubed is about 3 weeks. It'd be 1/1000.
Yeah.
So if you stay inside for 2 days and then just kind of hang out, don't go outside too often for 2 weeks, you're fine. But the first 7 hours, high.
Yeah.
Because you can get those in like 10 minutes.
Ugh. It does not sound like fun.
Thank you.
Oh, you're welcome. You guys have questions or?
Nah.
Oh wait, did you guys want to have a problem session?
Yes.
Oh
Yes.
Next week though.
Oh, you want to do next week? Okay.
Or just
We
anytime
can do
that's
it
not
now.
right now because I have to go catch a
Okay.
bus.
Okay.
Adios.
Do you?
With her.
Oh, okay.
Yeah. Okay. Next week, please.
Next week. Sure. of
Thank
course.
you.
Yeah.
I'll send emails out.
Thank you.
And then it'll be every Wednesday too. At least it'll be offered every Wednesday.
Oh, okay. Oh, okay. I like that.
Question?
Can I come into your office?
Yeah, of course. You wrote me about it, didn't you? Or did you write me? Or is it, I'm thinking it's Do you mind if we go to the Astro Lab though? Because I told people I might have a problem session. If anyone shows up, I'd want to be there.
What's a problem session?
That's when I solve problems and then people ask questions and. Oh, I'm still recording.